Hello and welcome to today's lesson looking at superconductivity. In today's lesson, which is part of the AQA A Level Physics course, we're going to try and understand the physics behind superconductors. Now, if we're being successful and learned in this particular lesson, we're going to understand and define what superconductivity is, describe what we mean by persistent current and critical temperature, and then look at different applications of superconductors working. So this links into the following part of the AQA A Level Physics specification. We're going to focus predominantly on the superconductivity properties of certain materials and the applications of superconductors. Now, in previous lessons, we've considered the concept of resistivity. So resistivity is basically the resistance of a 1 meter length and a 1 meter squared cross-sectional area of a material, and it's measured in ohm meters, which is an important quantity to use when we're looking at conductivity. Now, fundamentally, it's a measure of how much impedance a material produces against electrical current. Now, it's a much more useful quantity than resistance, as the resistivity of a material is the same regardless of its dimensions. So it's a quantitative measure of how much a mobile charge carrier is prevented from moving in the current through a particular material. So whilst the dimensions of a material can affect the resistance, the resistivity is not affected by the context of the material. So that's a very, very useful quantity, as it allows us to identify unknown materials, as resistivity is the same for all materials in every situation. Now, resistivity does not incorporate temperature, so therefore temperature can affect the resistance of a material and therefore its resistivity, which is why we always quote resistivity at a certain temperature, the most common one being room temperature, 20 degrees Celsius. But how does resistivity change with temperature? Now, there are three types of material where we need to consider how temperature affects resistivity: conductors, semiconductors, and insulators. Now, we've covered conductors before in the course. So basically, when mobile charge carriers flow through a material in the form of current, they collide with metal ions. These collisions cause vibrations, which in turn dissipate energy to an internal energy store, which is resistance. So for a conductor, the higher the temperature, the greater the ion vibration, the more collision between ions and charge carriers, the higher the resistance and the higher the resistivity. And conversely, the lower the temperature, the smaller the ion vibrations, the less collisions with the mobile charge carriers, so the lower the resistivity, because less energy is dissipated to the internal energy store that surrounds us. So in a conductor, when temperature increases, the metal ions vibrate with a greater amplitude, so there are more collisions between ions and the mobile charge carriers, so it increases resistivity. So when temperature increases, resistivity increases as well. But you can also consider semiconductors, such as thermistors. So in this example, a temperature of a thermistor can affect the resistivity of the thermistor, and an LDR, or light-dependent resistor, which basically is a component which can change resistivity due to the external conditions, which is a light intensity. So in this example, the intensity of radiation hitting the LDR can affect the resistivity of the LDR. Now, how do they vary in the particle level, and what explains this difference? So a conductor is a material with lots of mobile charge carriers in its atomic structure. It has enough mobile charge carriers to form a current when a potential difference is placed across it. An insulator is a material with very few mobile charge carriers in its atomic structure. In theory, a perfect insulator has no mobile charge carriers, but we've never observed a perfect insulator in the universe. Now, an insulator does not have enough mobile charge carriers to form a current when a potential difference is placed across it, because the mobile charge carriers are so tightly bound that no energy can liberate these energy carriers. So conductivity and resistivity in an insulator is unaffected by temperature. Now, a semiconductor is a material with a reasonable amount of mobile charge carriers in the structure, and also, very importantly, it can change how many mobile charge carriers it has in its structure. Now, you can change the number of mobile charge carriers in a semiconductor by carrying out work on the semiconductor. So, for example, a thermistor. Now, in a thermistor, the majority of the charge carriers are not mobile, they are fixed in the thermistor. But it can actually release these charge carriers if work is placed into the thermistor. So in a thermistor, as the temperature increases, the resistance and resistivity decreases, because when work is done into the thermistor, i.e. temperature increases, the thermistor releases more mobile charge carriers, which increases the current and decreases the resistivity. So the increased energy allows some of the charge carriers to leave the thermistor structure, join the other charge carriers in the metal wire, lowering the resistivity. So in a thermistor, the higher the temperature, the more mobile charge carriers released by the thermistor, because this work done into the thermistor has liberated the charge carriers to become mobile, so it increases the current, decreases the resistivity. Now, that's an application of something called thermonic emission, the emission of particles due to work being done into the surface of the material. Now, whilst there are more mobile charge carriers in the circuit and therefore more collisions, you might argue, well, does that not increase the resistivity? Well, that effect is swamped by just the number of mobile charge carriers that have been released by the thermistor. Now, therefore, the overall effect of adding more mobile charge carriers from the atomic structure decreases the resistivity and increases conductivity. Now, the effect is also noticed for the LDR, however, the work provided is not by thermal energy, rather radiant energy, electromagnetic radiation. So we can show this in the following graphs. So for a thermistor, we notice that at a low temperature, there's little work done to the semiconductor, so there are fewer mobile charge carriers in the circuit, so you've got a high resistance. But at a high temperature, there's been lots of work done to the semiconductor, there's many mobile charge carriers, and there's a low resistance. So we call this a negative temperature coefficient thermistor. So these are the only thermistors we cover at AQA A Level Physics. And it's also the same for an LDR, that at low light intensity, there's little work done to the semiconductor, there's very few mobile charge carriers in the circuit, so you've got a high resistance. And when you have a high light intensity, lots of work is done to the semiconductor, there's more mobile charge carriers in the circuit, you've got a lower resistance. So to contrast that with the conductor in a semiconductor, when temperature increases, there are more mobile charge carriers because they're being liberated from the structure when work is done into it. So there's more mobile charge carriers. Okay, this will give you an increase in conductivity and a decrease in resistivity. So it's the opposite to a conductor. Now, there is also a fourth category of material. So in addition to conductors, insulators and semiconductors, there's also a category of materials called superconductors. But what are superconductors? What are the uses of superconductors? And what's the physics behind a superconductor? Well, when a metal is cooled, the amplitude vibrations of the ions of the material are reduced. So these electrons or mobile charge carriers will lose less energy as they travel through the material because there's less movement and from the ions, there's less collisions, so it reduces resistivity. So it was considered, well, what would happen when a metal reaches absolute zero, okay, the lowest temperature possible? Well, Lord Kelvin hypothesized that at 0 Kelvin, when there was no energy in those ions, the mobile charge carriers, okay, would stop moving, there'd be no conduction, and a perfect insulator would be achieved. However, this was not observed. Another effect was observed. The phenomena of superconductivity was observed in certain materials. Now, a superconductor is a perfect conductor of electrical current. A closed loop of superconducting wire will continue to carry the same current constantly because there's no resistance. Because a superconductor, by definition, is material with no resistivity and therefore no resistance. Now, a superconductor loses all its resistivity as below a certain temperature there are no collisions between the material ions and the mobile charge carriers. So there's no collisions to alter the path of motion of your mobile charge carriers, so there's in fact no resistivity. Now, not all conductors will become superconductors at low temperatures. Now, some materials just can't prevent collisions from occurring between ions and charge carriers. Now, the temperature at which some conductors will transition to a superconductor is called the critical temperature. Now, the critical temperature is a different value for each superconductor material. So there's just not one set critical temperature, it varies on material. Now, the work on superconductors started with a scientist called Ons. Now, Ons discovered how to liquefy helium, which was happening at about 4.2 Kelvin in 1908. Now, when he worked this out, this allowed physicists to study how materials behaved at low temperatures because he could immerse substances in liquid helium and lower them to that temperature of 4.2 Kelvin. So he immersed materials in liquid helium and cooled them to very low temperatures because he wanted to observe the material properties of materials at these low temperatures. Now, in 1911, Owens discovered that when mercury was cooled, when placed inside liquid helium, at a temperature of 4.15 Kelvin, it becomes a superconductor. So these were the experimental results of the resistance of mercury when it was cooled. It was found that the loss of resistivity didn't occur gradually, but it's that these materials, such as mercury, lost resistivity suddenly. Now, the temperature at which the substance loses resistivity and its resistance is called the critical temperature. So the critical temperature of mercury we found occurred at 4.2 Kelvin. So it's denoted by a sudden drop in the resistance in the graph. Now, a superconductor will only exhibit superconductivity when it's below a certain temperature, which we call the critical temperature. Now, below the critical temperature, the current going through a wire of the material stays at a constant level because there's no resistance to reduce it, so it's called a persistent current. So the critical temperature is the point on the graph where the resistivity or resistance drops massively and the persistent current occurs below the critical temperature. Now, just as a little aside, pure metals such as mercury show a sudden drop, whilst alloys and ceramics show a slight curve, as this occurs because they are compositions of different materials, so we'll have a slight difference in properties. Now, not all conductors will act as a superconductor, so there's a pronounced difference between the resistance temperature graphs of conductors and superconductors. Now, it's always been the aim of physics to find materials which have a critical temperature similar to room temperature. Now, several other metals, apart from mercury, exhibit superconductor behavior, as do some components, and so do many alloys. Now, some of the components were recently discovered since in the 1990s. We can actually find superconductors at relatively high temperatures. Now, that's actually easier to carry out because this allows physicists not to use relatively expensive liquid helium to cool the material down, but the cheaper liquid nitrogen to get them below the critical temperature. Now, this allows physicists to carry out more research on superconductivity and is a more affordable application of superconductivity. Now, the relative breakthrough of the materials with the higher critical temperature is important because it lowers the cost of producing a superconductor, because liquid nitrogen is a lot cheaper than liquid helium, so the higher the critical temperature, the cheaper it is to produce and the easier it is to produce. Now, currently, the highest critical temperature recorded for a material is minus 110 degrees Celsius. Now, that is obviously still extremely cold and a lot colder than room temperature, but it's a massive improvement compared to what we had originally in 1910 with things like mercury and lead. Now, in 1987, Bednos and Muller from IBM won a Nobel Prize in Physics for their discovery of a new superconductor which had a relatively high critical temperatures. Now, scientists, even to this day in 2020, are keeping researching ways of having superconductors as high a temperature as possible, even close to room temperature, because the closer it is to room temperature, the critical temperature, the easier and cheaper it is to make a superconductor. So here are some examples of some superconductor materials and their critical temperatures. And just remember, the closer to room temperature the critical temperature is, the easier and cheaper it is to turn into a superconductor. So while zinc has a very low critical temperature, it's hard to make it into a superconductor. The thallium, calcium, bismuth, copper oxide compound or an alloy in this example has a relatively high critical temperature of 125 Kelvin, so it's a lot cheaper and easier to turn into a superconductor. Now, pure metals like mercury and lead have a low critical temperature, so therefore our future superconductors is in ceramics and in alloys which have a much higher critical temperature because they're much closer to room temperature. Now, superconductors have two main properties which makes them really useful in the real world. Okay, now number one, like we mentioned before, the superconductor can maintain a constant and large current with very little energy losses due to resistance. So it makes a superconductor very efficient. And secondly, because the conductor can also be an electromagnet, as all conductors will also produce a magnetic field, a superconductor is also an electromagnet. Now, because it can make a large current easily, because there's no resistance to current flow, it can make a very strong magnetic field easily. So if you want your conductor to make a very large magnetic field, it's better to have a superconductor as opposed to a normal conductor. Now, there are many applications of superconductor materials in 2020. So things like MRI scanners. Now remember, all superconductors are used because they dissipate little energy to the surroundings, because there's little energy loss due to resistance, and they produce strong magnetic fields. Now, for an MRI scanner, they work because there's large concentric circles of a superconductor material, which is normally niobium titanate, kept cool with liquid helium. Now, for an MRI scanner, a tank containing about 1,000 litres of liquid helium is needed, and it has to always be kept below 4 Kelvin because that's the critical temperature. So the coils and the helium are cool below 4 Kelvin. They're then thermally sealed, and it stays at the temperature of about 4 Kelvin for 10 years, which is the lifetime of a typical MRI scanner. Now, if the temperature of the helium rose, that would mean that the coils would lose their superconductivity, the magnetic fields would not be very strong, and the machine would be useless. Another example is in things like supercomputers, in things like electrical power cables. Now, in fact, the world's first commercial superconducting power transmission cable came into use in Germany, in Essen, in 2014. Now, these cables are cooled by liquid nitrogen and can therefore carry a current 5 times larger than traditional copper cables because there's no energy loss due to resistance. So the current can be as high as possible. Now, this means that any energy has to be minimal. Now, around 7.5% of the UK's electrical energy is actually currently wasted as heat in the wires and the transformers of our national grid. Now, if the transmission cables could one day be replaced by superconducting cables, the energy savings would in fact be huge, and there'd be less need for a transformer because the transformers are there to decrease the current in the transmission cable to reduce energy loss due to resistance. That would not be the case if you had a superconducting wire. So it's a possible look in the future of our national grid. Another application of superconductors will be something like a magnetic levitation or maglev train. Now, these trains can travel at much higher speeds than normal trains because there's a lot less friction because the wheels aren't touching the ground. The train is in fact levitating above the surface due to the strong magnetic fields of the superconductor. So there's no friction that way, so therefore can travel a lot higher speed. Another example of where superconductors are used are in things like particle accelerators. Now, powerful superconducting electromagnets are used in the LHC to steer things like protons around the huge circular tunnels. Now, in the particle accelerator, the electrical field is used to accelerate the particle to the correct speed because it acts in the same direction as the motion of the particles, whilst the magnetic field of the electromagnet is used to deflect the particles in the correct path because the magnetic field acts perpendicular to motion, which is something we'll look at in the electrical and magnetic fields topic in the second year of A level. So the applications of superconductors in the real world involve maglev trains, MRI scanners, particle accelerators, both synchrotrons and cyclotrons, electrical energy generators, fast electrical switches, and superconductors. So, we've currently looked at what a superconductor is, the definition of critical temperature and persistent current, the useful properties of superconductors, and the uses of superconductors in 2020. Now that is everything you need to know for the AQA A level specification. So if you just want to learn about superconductors up until the A level examination specification, please stop the video now. However, we can also just consider the following important questions. So what turns a conductor into a superconductor? Why don't all materials act as superconductors at low enough temperatures? And what's the physics behind superconductors? Now, can I just stress the answers to these questions are beyond the A-level specification. However, you may want to consider this because it's an interesting part of physics to consider. Now, we can consider the material of a conductor to be formed from a lattice of metal ions. Now, mobile charge carriers flow through this metal ion lattice when a current flows. Now, when the electrons flow through the material and form a current, they bump into the lattice of the ions. These collisions cause vibrations, which in turn dissipates the energy thermally. So it's these lattice vibrations which give a material its resistivity properties. So the collisions between the metal ions and the mobile charge carriers lead to resistance. Now, the metal ions in reality are not stationary, they vibrate about a fixed point. The amplitude of said vibration is determined by the temperature of the substance. The higher the temperature, the greater the amplitude of vibration for the metal ions. The lower the temperature of the material, the smaller the ion amplitude vibration. Now, for a conductor, the greater the ion vibration, the more collisions, the greater the resistivity. And the smaller the ion vibrations, the fewer collisions, the smaller the resistivity. So like we said before, for a conductor, the lower the temperature, the smaller the resistivity. So in theory, you would suggest though that even if you cooled a material down to absolute zero, there should still be some resistivity. Because at absolute zero, yes, there won't be any ion vibration, but there still should be a chance of collision between the ions and the charge carriers, because those mobile charge carriers could just hit into a stationary ion. Now, how does the superconductor remove this possibility? Well, how it works is that the lattice vibrations themselves are actually responsible for the free passage of current, because when the temperature of a material decreases, the lattice bonds increase in strength, because that fixes the ions into a position and restricts their vibrations. Now, some conductors, this can actually take a long time to occur, relatively. So as the material is cooling down, it can actually take a bit of time for those lattices to actually form those strong bonds to fix those ions into position. Now, this delay causes the lattice formed to be distorted. Now, that's why certain materials can act as superconductors, because if it takes a long time for the lattice bonds to strengthen, it is a superconductor. If it takes a very short time for the lattice bonds to strengthen, it doesn't act like a superconductor. So you get basically a distorted lattice structure for a superconductor. Now what happens is, in a superconductor, at low temperatures, the mobile charge carriers, the electrons, team up into pairs and travel through the lattice without any collisions with those ions. Because as one electron passes through the lattice distorts towards that particular electron, because it creates a tunnel of positively charged particles. Now the lattice is attracted to the negatively charged electron. So what will happen is it will form a positive charge area because there's lots of positively charged ions. So therefore, every other electron that therefore travels through that lattice will be attracted to that area of positive charge because negative and positive charges attract. So therefore, this attracts the second electron, which will pass through the same path as the first one. Now, because it's already gone through that path, it's in essence cleared the way for any further electrons to travel through that path without any collisions. Now, the lattice can't collide with the negative charge carrier as it has no energy to carry any vibration. So whilst it's attracted to the negative ion, it can't in fact collide with it because it has no further energy to actually hit it. Now this creates a tunnel in the lattice with the positive charge at the end. This positive charge attracts the other negative charge carriers to move through the same tunnel, as such like that. So it produces a negative charge carrier stream, and there's no charge carrier collisions with the metal lattice because they'll all move through this tunnel because they're all attracted to that positive charge, and those positively charged ions can't in fact collide with those negative electrons because they have no energy to move any further. Now, when the lattice is distorted, you actually find that small pockets of sound waves called phonons, okay, are created, and when pairs of electrons travel through there, which we call Cooper pairs, okay, we can actually say that one emits the phonon and the other one absorbs the phonon as well. Now, so like we said before, as the negative charge carriers move through the lattice, they become linked, so we call those Cooper pairs. So it leads to an electron emitting the phonon through the distortion and then gets passed through the distortion and absorbed. But that's beyond the A-level specification. Now, just to clarify, what summary need to know for the A-level specification, that superconductivity is a property of certain materials where you have zero resistivity at and below a critical temperature, which depends on the material, and the applications of superconductors include the production of a strong magnetic field and the reduction of energy loss in the transmission of electrical power. So if you've learnt in today's lesson, you can define what a superconductor is, describe what persistent current and critical temperature are, then look at applications of a superconductor working. I hope you've enjoyed today's lesson on superconductors, and I hope you have a lovely day.